Yeah, in that somewhere. There is a control of that. My mind goes along. Yep, so I picked it. I submitted some slides with a lot of yeah. We'll have more slides with less information, but that's not normally my style, so I'll practice that. Because each of these slides is like a minute and a half. Yeah, it's good. Move words.
Yes.
Yes. You're expected apparently in the room with the jury.
I'm there.
Ah, okay. Okay.
Yeah, okay.
Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you to the public defense of Mr. Florian Driessen. Mr. Florian Driessen has presented to the faculty this PhD thesis on the topic, the line shadowing instability and its effects on wind clumping for OB stars, in partial fulfillment of the requirements for the degree of PhD in science, astronomy, and astrophysics. He shall now publicly defend his PhD thesis. Mr. Florian Driessen, you are now invited to give presentation which will last about 45 minutes about your work. And afterwards, the examination committee will ask questions and discuss your work with you. Please. And also welcome everyone to this public defense.
Okay, great. Thank you for coming. So I'm very glad I can be standing here because that was not clear for a long time. So for the people who are starting a defense next, so never go to a conference just before your public defense. So you might actually have problems then. So as Yasmina said, so my topic is on the line shadowing instability and the wind clumping for these styles. So there's a lot of nasty words there, but basically you can imagine it as a physical process, like an instability that causes some kind of phenomena, which are the clumps that happen for a specific type of stars, which are OMB stars in this case. So I will explain to you all of these things. I hope it will be clear after 45 minutes. So I will do my best. But what we really did actually is that this PhD is studying how this instability behaves under different types of physical properties of the star, meaning a difference between stars, so O and B, what the effect is of a magnetic field, and also what the effect is of the metal content of the star. And so this will be outlined further down the road today. Now, but we will first start with the most fundamental concept as underlying every physics here. That's that of a stellar wind. So I will start to explain to you what this means. And for that, I will actually start with a comet, so close by in our solar system. So you might have heard in school, you've learned that interplanetary space is empty. But still, if you look at a comet, it has tails. In fact, it has two tails. So if interplanetary space is empty, there is no air, there's no forces, there's no friction. So the comet shouldn't have a tail. So still there are two tails. But what they didn't learn you in school is that the sun is actually ejecting particles. It's ejecting particles all the time. And these particles interact with the comet and provide a force that creates a tail-like structure when the comet revolves around the sun. So this continuous outflow of particles, that's what we call a stellar wind. In case of the sun, we just call it a solar wind, because the sun always needs different nomenclature for the thing. So that also makes a crucial difference with winds here on Earth. So we as on Earth, when we talk about winds, so we mean something that's flowing parallel to the surface of the Earth, so an air parallel to the surface. For a star, so a stellar wind, we actually mean the opposite. So we mean a flow opposite to the surface, so perpendicular to the surface of the star, away from the star. And of course, you now immediately see perhaps the issue, so that if I throw up something here at Earth, it falls down again, and the same would happen at the star. So there's some kind of agency that's able to lift the material out of the gravitational well of the star and initiate an outflow of particles, or just really the outer envelopes of the star. So the star is continuously losing mass. Now for our sun, you may say, okay, we don't feel this, and I would totally agree with you, because our sun is actually, in its 10 billion year lifetime, it only loses about 1% of its mass. So that's nothing on a human time scale, 100 years, say, for example. So we don't feel this. But there are other types of stars where this process is actually much more violent, and the stars are able to lose much more mass, even 60, 70, 80% of their initial birth mass. So that's quite a lot, which will change the environment of the star, as we will see. So you can classify the winds, outflows, the stellar winds from stars in a kind of two classification scheme. So first of all, we have our sun. So these are classified in the coronal or pressure-driven winds. And so that's just, the solar wind is just actually the expansion of a hot gas. And we call this a Parker wind after the guy who first theoretically analyzed that. And there's more luminous stars, much more larger than the sun, but actually also cooler. So there are supergiants. There's not entirely clear what's going on, but recently it was proposed that turbulent pressure near the surface of the star is actually causing, helping the star to get rid of its outer envelopes. And then we have a second class, which is rather broad, as of the radiation-driven winds, so what we will be discussing today. So there's, first of all, the OB stars, so they have line radiation-driven winds. And I will come back to that very soon. Last Friday, you may have seen a PhD defense on Wolf-Rayet stars, so they also have winds, but there it's less clear actually what's going on. We think it's a combination of this line radiation and what we call continuum radiation. You can also see Lucas' PhD defense of last month to learn more about that. And of course, also well studied in our Institute DHB stars, where it's again radiation that's now impacting on dust grains, launching an outflow. But here, also near the star, it's not very clear what's actually lifting the material out of the gravitational realm. So pulsations are followed as a mechanism, and another one is past the convective motions of the star. So that's still an open question. So let's focus on these line-driven winds from all these stars. So what is this? So as I just mentioned, so they are a class of the radiation-driven winds, and there are many reasons why you would like to study them, of course, radiation-driven winds. Because first of all, in most astrophysical systems, you can make 3D pictures about them, because the radiation field is so strong that emitted from the object, that the local environment of the object will change. So the dynamics will change near the object, which may even change the chemical content surrounding the object. And this happens really on all scales in our universe. So from very small, when the stars are born, to more standard scales, I would say, of stars, where stars have stellar winds during their entire life. The end of their life, they even can have supernovae. And of course, even on a larger scale, you can have galactic outflows, which can be quite violent as well. So there's plenty of reasons to study this. So we will focus on the stellar winds of OB stars. So what are OB stars? So here's a standard classification used in astronomy. As you can see, the lettering doesn't make any sense. So you may think that the classification here is based on this figure on the size of the star is actually not correct. So it's a classification based on the temperature, the surface temperature of the star. So the O stars are the hottest in our universe, at least for these stars here, and the M stars are the coolest. Now, as you can see on this figure as well, so the stars have different colors, and that's because we can relate temperature with color. And if you have ever been in a shop selling LED lights, you may actually have played with this like I did, because LED lights can have different colors, and that's basically because the temperature of the light bulb is changing. And this scheme here basically comes pretty well in reproducing the temperatures of the stars below. So the A stars are about 10,000 degrees Celsius. Our Sun, which is a G-class star, is about 6,000 degrees Celsius. Although it's mentioned here in Kelvin, it's a different temperature scale we use, but it's basically almost the same as degrees Celsius on these scales. But as you can see as well, so the old V stars don't fit here. And that's first of all because they don't sell such hot LED lights in the store. Because those stars can reach temperatures of 20, 30, or even 40,000 degrees Celsius at their surface. So it's pretty hot. And this heat has an important consequence, as we will see soon. But I first want to discuss very briefly the evolution of such a massive star, OB star, because this differs from our sun. And I don't want to focus on the sun here, but in order to become an OB star, you at least need about 9 times the mass of our sun. And if you have that, you will basically end up as a supernova. You will explode to the supernova and become either a neutron star or a black hole, depending on your initial mass. Now the problem here is that this evolution is very uncertain, so we don't really know how much mass these stars are losing during this entire lifetime, which spans just a few million years. For our sun, it's more than 10 billion years, so they live quite fast. And that's all because of their line-driven winds or their radiation-driven winds. And the heat of the star that I just mentioned is here the key ingredient to actually make the wind happen. Because what happens, the hotness causes ions, so they're not neutral, like here on Earth, like this table, for example. They become ionized, so electrons are stripped away from the atomic nucleus. And these ions, they will start to interact with the line-driven wind, so with the light actually from the star, causing a line-driven wind. And it's especially specific lines that are very important here, and those are those of iron. So there's a small figure here of iron shown. So these are just 2 ionization stages of iron. But you see there are many possible transitions. So the light of the star can interact in many different ways with such an ion, which is actually a very powerful way to generate a wind outflow and overcome the local gravity of the star. So how does this work in a somewhat more conceptual way? So imagine your star that's shooting up photons or light. These light particles, they can only interact over a very narrow zone, so they need to have the correct energy to interact with the ion. If they have, they will impart their momentum on the ion, and so it will get a net outward push. Now, the particle will go farther away from the star, but then it needs to interact again, otherwise it may fall back if it has not received enough. And the question is, are the same photons or the same light particles able to interact with this gas particle? And the answer is no, because there's a very important effect here, namely the Doppler effect, which actually shifts the ion frequency. So the ion will start to interact with light of a different frequency or a different energy. For example, the yellow particles, and then the process repeats itself again. And then later the light will interact with even photons of different energy again, so just the blue ones, for example. And this will generate a smooth wind outflow starting at the star of a few kilometers per second, going up to a few thousand kilometers per second, typically 2,000 to 3,000 kilometers per second. So that's quite fast. Now, of course, we forgot a small detail here in this whole physical process. Namely, there's an instability, and it's again the Doppler effect that's the problem of this whole mess that's going to be created. And you can kind of conceptualize this. Because if you look up what an instability is according to the dictionary, you kind of find something like political economical instabilities, and yeah, that's certainly true, but that's not what I understand for the instability. So a physicist would call this somewhat different, namely a fast-growing wave or a disturbance that happens in a fluid or a plasma. So, and this happens in our daily life quite a lot. If you drink coffee, for example, with milk, or if you cannot cook soup, this may happen. But they also happen in astronomy in a more technical way. And one of them is this famous liney shadowing instability. So how does this kind of work? So I'm going to try to explain this very briefly. So consider again our wind outflow, our monatomic wind outflow in velocity. So high velocities far away from the star, slow velocities near the star. Now, of course, the atmosphere is not static like in Earth. There's some small kind of turbulences here and there. So turbulences you can mathematically model as a wave. So just take a wave in this atmosphere, and we're going to see how it evolves. Now, the problem with the Doppler effect is the wave has a curvature. So some parts of the wave will receive more light from the star than other parts. And the wave will start to grow, and the atmosphere actually will slowly and gradually start to tear apart, because what happens, this wave gets basically stretched and stretched and stretched until things start to run into each other. And this runaway process that's caused, that's what we call the shadowing instability. And this deshadowing really captures the essence of the underlying physical mechanism. You can kind of imagine it if you have a queue of people, and someone in the front shines a light. So if somebody is standing in front of you, you see some light, but you don't see the source. However, if you go out of the shadow caused by the light, the person in front of you, you will actually see more light, and you might be able to see the source. And it is the analogy you can more or less make the same, because the light now shining in front of the cube is the star, and the cube in front of you are just ions in the wind outflow. So this runaway process you can theoretically model. In 1D, it kind of looks like this. So you see on the top velocity, and in the bottom the wind density. So they're monotonically increasing and decreasing functions of position away from the star. So this is the smooth wind predicted by our standard theory of line-driven winds. So what happens if you turn on the instability? So the wind, like I just said, gets torn apart, and there's a lot of structure formation going on. You see discontinuities all over the place, both in velocity and density space. And this is what we kind of call the wind clumping. I'll just show you this too. So notice that once it sets in, it also doesn't go away again, so it just keeps producing the same mess all the time. So if you take a static picture of this movie, so you can distinguish two types of structures in this outflow. So on the one hand, you see very high density material, or these higher than the rest in the wind, which are the clumps, but they're moving quite slow compared to the original outflow. Well, on the other hand, you have a total anti-correlation for the other component, namely it's a low density gas, which is moving quite fast. So we get this picture here of clumps embedded in a very diluted medium. And you can statistically characterize this as well by counting the amount of overdensities, which is just captured in a factor F, which we will use several times in the remainder of this slideshow. And now why you want to do this? That's because these clumps, they will actually affect the way you see or you learn about the local conditions of the star and the wind. So if you want to learn about that, you need to take them into account in your observational models, otherwise you will infer incorrect information about the star or the wind. It's mainly the wind actually. So in 2D, of course, this looks even denser. It's the same. So now you see on top density, on top of the velocity. And once the initial wind is washed away, you get this fragmentation of material, which you have in density space high, red material, which is embedded in this smaller blue part, which is the high density, the low density, high velocity gas. So you see really this very nice filamentary structure arising. So of course, like I said, that's important to learn. Of course, the movies are also nice, but that's not the main reason we do this type of stuff. Because how can you learn from the star? That's by studying what you receive from the light. So for the sun, we are lucky that we can send out spacecraft and we can actually measure what the sun is doing quite well. For a star, this is not possible. So one way to learn about the star is measure the amount of light you receive on Earth, and it's typically called a spectrum. So this would be in the ideal case the spectrum, so it's just how much brightness at some wavelength you measure. And now, of course, as in the ideal world, the stellar light will interact on its way to Earth with different physical things, and so you will get gaps and peaks in your spectrum, which correspond to absorption and emission processes at some type of wavelengths or energies. And it's these gaps and peaks that are actually affected by the presence of these clumpy structures in the room. And so there's one important theme here, and I mentioned briefly during the stellar evolution slide that we don't really know the mass loss of these stars. And so we need to constrain, or we want to constrain it as best as possible, the degree of mass loss in a certain evolution phase. Now, there are some lines where you can derive mass loss rates from by studying the stellar wind, but you're not really deriving the mass loss, you're actually deriving the degenerate quantity because you're deriving the product of the mass loss and the amount of clumping, the amount of overdensity in the ring. So this is a problem because typically you don't know this square root factor, so you assume it's 1, so it's a simple scale, but you're absolutely off, or you need some kind of theoretical model, so what we're doing, or you have very nice spectra and good observation that you might be able to constrain the clumping as well from your observations. Or you have a nice genetic algorithm where you can also get this from. So let's see how this instability, so how this line shadowing instability behaves with stellar properties. And we will first look at the OMB stars. So I mentioned, so these are the hottest, but they're not the same temperature. So the O stars are the hottest, the B stars are somewhat cooler, so they're still around 20,000 Kelvin degrees Celsius. So that's a lot. So our question here is like, do the clumping properties in differ between these stars? And if so, to what degree is that the case? Because in the literature, there's no real idea about the clumping properties of these stars, and actually, if people were using clumping for these stars, they were just assuming either nothing or they were assuming the O stars. So one needs to check whether this is true. And here you see the difference in the wind structure, velocity and density space again, between an O and B star. So these are 2 models we studied, and we had some more models, of course. But this is essentially the hottest O star and the coolest B star in my sample. And so first of all, the notice is that the dashed line here is, again, the smooth wind that we predicted from standard theory. So no instabilities. And you already see that the B star has a much slower wind outflow than the O star. So it also its density stratification remains somewhat higher. Now, if you have the instability, you can clearly see the difference here, because in velocity space, the B star is unable to provide enough shock formation, which results in density space immediately to less compression, and as you can see from both these figures. So you might already find or think that the clumping properties differ between O and B stars, and yes, you're absolutely right. So the question now is to what degree do they differ? From that, so we can just compute this from the simulation. It's more or less a free output parameter for us. So on the left, you see the radial stratification of this amount of overdensity away from the star. And you already see that there's a difference in shape, and there's also a difference in the magnitude that's reached between the O and the B star. So they do indeed differ. Now, you cannot really use a radial stratification in your observations. So what we typically do is that we take one number, so we take some kind of average factor, and we can compute an average, which is done in the second and third panel for the entire length and for a specific line, for a specific spectral line, which is the hydrogen alpha line, that's often used to infer mass loss rates from massive stars, so from OP stars. Now, it's clear from this figure that the B stars have much lower clumping than the O stars, and it's typically a factor 4 to 5. So you better not using O star clumping corrections for your B stars, because you would reduce the mass loss to too much, no more than necessary, because they're almost smooth, so you don't really need a correction because the clumping is essentially almost unity. Okay, so yeah, that's what I just said. So then there's a second point, which is the metal content of the star and its surroundings. So to illustrate this a bit, so the metal content, or the metallicity as we call it, in astronomy is essentially a measure of the metal abundance. And metal here means anything more than helium. So basically in this table with elements, everything except the first row with the first two elements. Now I don't want to give a lecture on cosmology, but so our universe started with mainly on hydrogen and helium. So all these heavier elements, they were forged inside stars and expelled during their lifetimes because of the stellar wind and because of explosions potentially at the end of their life. Now the problem is if you have less metals, remember that line-driven winds are mainly metallic because of metallic ions driven, you'll get weaker winds. And if you have weaker winds, you have also less mass loss, so the stars are losing less mass in environments where the metallicity is lower. So either in the early universe or some parts in the present universe where there's just low metallicity. Now the question here is, of course, what about the wind clumping? So how does this depend on the metallicity of the star and its wind? So we set out to investigate this. Now you can constrain from observations, a relation between how the mass loss of the star should depend on the metallicity. So you can actually also do stellar evolution across the cosmic time as you want. Now, this relation turns out to be a power law, but there's a key problem. So observations that use this type of the constraints, they actually use spectral line information that's sensitive to the clumping phenomenon. So what they're really deriving is this quantity. And of course, here it's assumed that f is again 1, so square root of 1 remains 1. So you get this population. And so we can do this in our neighborhood, actually calibrate this relation by looking at two satellite galaxies. Our Milky Way, this is called the Large and Small Magellanic Cloud. So they're galaxies with lower metal content than our own Milky Way. So there you can derive and establish such a power law relation between mass loss and metallicity. Now the question now is, does this clumping factor, so this factor F, also behave in a power law fashion on metallicity? Because if that's the case, it's very simple, it's plug and play in this formula, and you can actually find how the actual mass loss should be behave as a function of metallicity. And can imagine that it is, so, but it's a very weak dependence. So if you plot, so from our models, we run a bunch of models, if you plot an average quantity in the wind as a function of metallicity, we have metallicity proxy in our case, or different quantity that relates to metallicity, you'll find in logarithmic space a straight line if you fit it, which means that in normal space that becomes a power law, and this power law, like I said, is very weak, is very shallow, which means that if you have these studies in other galaxies with less metal content, your correction to the mass loss metallicity relation is actually quite modest. Because if you take the square root of this quantity, the orange box, you don't have really much left. So your original statement is more or less unmodified, which is interesting and nice. And this is something we can actually currently check with an ongoing observational campaign. And then last but not least, of course, the magnetic fields, the most beautiful thing. Now, if you want to talk about magnetic fields and massive stars, it's somewhat confusing because, first of all, only 7% of Milky Way has a large-scale magnetic field. So whether they have small scale, we actually don't know at all. But 7% has a large-scale magnetic field. From a stellar structure point of view, that's strange. So we take this for granted, this fact. So we just take our star with its wind, and we pull a magnet inside it. So what happens then, you get a magnetosphere. And this magnetosphere is different than the magnetosphere from Earth, because now the wind is pushing outward. It actually starts to fill the magnetosphere. And here is a small dichotomy then occurring, because depending on the star, whether you're O or E star, there's a different type of magnetosphere arising. Because the O stars turn out to be slow rotators, while the D stars turn out to be fast rotators, which causes a small change in the appearance of the magnetosphere. But here we will only discuss O stars, so we will only see later the top type of magnetosphere. Now, we have this magnetic field then, so we take this for granted, it's there. So we want to understand now, how does this instability from the radiation field interact with this magnetic field? And you can do this from a purely mathematical point of view. And this is probably going to be the most obscure slide of the whole presentation, so my apologies. But what we essentially do, we consider a magnetic field, and we consider a wave. So like I mentioned earlier, we can model fluctuation in the atmosphere as waves. So, but a wave can have a certain orientation. So it can have, at this state, a certain orientation with respect to the magnetic field axis. If you do that analysis, you can find that waves with a short wavelength, they actually do some very funny things. So they're causing the instability, but they're also causing the magnetic field to do, or the waves from the magnetic fields to behave somewhat different. And that's what this figure tries to explain. So these are actually solutions of an eigenvalue problem. So you see 6 solutions, only because there's some overlap, you see actually only 4 curves. And what's only important here to realize is that there's a part in this diagram where there's an instability when things are bigger than 1, and that's the line shadowing instability. So this wave remains unstable in the presence of the magnetic field. But more importantly, there are other types of waves in a plasma. Magnetic waves, so the alphane wave and the fast wave in this case, which are smaller than 1 of their curves. And in this case, the physical interpretation associated with this figure is that they are actually being damped. And that's an interesting phenomenon, because it might actually change how these waves evolve into a non-linear regime, so the actual wind physics after the waves have become more or less rogue. So you can conceptualize this somewhat better in case for the alphane wave, because so the alphane wave is just a fluctuation of the magnetic magnetic field, but it moves as a transversal wave. So as the movie showing on the left, the field is horizontal here. So you can cartoonize this as well. So if we have only magnetic field, then we have a fluctuation. So this Alvin wave is just nicely traveling as a transversal wave. However, if the radiation field is there, what happens? So this radiation, these photons, they scatter around, and that effect actually causes some type of drag force, which you might visualize as some kind of phenomena where the wave dies out, so it's smoothly and gradually killed, essentially. So that's what the mathematical analysis shows, with many equations in general show, of course. But that's the key outcome. And this question is, how does this change for the future, the way we get the quantum properties from magnetic exercise that have an unstable reach. So you can also do numerical simulations of this. So we did some first. So on the left you see again the density of the wave. So on the left we see a normal star without magnetic field, no star. On the right you see the same one, but now with a dipole field attached to it from the magnet inside it. And if we turn this on, so what happens? So on the left, we see the same that happened before, as I showed you in the earlier movies. So material starts to fragment. So you get these small scale incoherent structures, which are the clouds, that are still embedded in this diluted medium, which is here colored in yellow. Now we look to the right, the situation becomes entirely different. So of course, here first of all, this magnetosphere that I just illustrated in the cartoon. So this will catch part of the wind outflow, and it will channel it along the field lines. It will collide in the equatorial plane, and most of it will actually fall back onto the star with some small leakage. But outside, the magnetosphere structure is much more different. As you can see, you don't have really small scale structure anymore, because it's rather incoherent, but the large scale coherent structures in the polar direction. So we visualize this also in aesthetic movie, an aesthetic mode, make the point. So you see on the left is again a non-magnetic model. So these are small scale clouds generated near the star with propagate outward. They may collide farther away from the star, so they can somehow be configured. But on average, they remain small compared to what's going on the left, on the right, which is the magnetic model, where you see now really filamentary structures that have kind of all type of sizes in the polar direction, and actually we call them pancakes because that's actually what they are, we think, at least how they look. So this morphology we see here may then affect the way we do studies of the light from the star, and so we need perhaps different types of corrections based on the output from these numerical simulations. That's something I want us to look into in the future. Which brings me to the end, actually. I'll do the summary and conclusions as you want. So it's very brief because we know everything about stellar winds now, of course. So the 4 key points we discussed here are essentially that we first looked how this line shadowing instability behaves as a function between O and B stars, and we saw it's different. They have different clumping properties. We're also seeing that the clumping properties change the function of metallicity, but it's not so strong. And of course, there are some pilot studies on magnetic fields that show, first of all, a purely mathematical analysis values that magnetic waves, shortwave magnetic waves, are actually getting killed by the radiation field, and that in a numerical simulation, these small-scale incoherent clumps become actually large-scale coherent pancake structures. So the question, of course, and this sounds perhaps like the obvious statement, but it's not, that you need theory and observation to constrain these properties further. And actually, for some of these parts, um, that we were agreeing on to do that, especially for the non-magnetic case to point 1 and 2. So having said that, I'm finished. I want to mention one more thing before we probably are going to clap. So I've always wondered the past 4 years, so I've said there many times as well, that you clap for the candidate in front. So I never understood this, because I'm standing here because of 2 great people, which are probably my supervisors, and I think that at least one of your hands should clap also for them. And having said that, I will also clap for my 2 supervisors, because without them, I wouldn't be standing here today for you. So thank you.
That was a very, very nice presentation. Thank you very much. Now, before opening the discussion, I would like to introduce the jury members. So I will start with Dr. Ronnie Bloom from Royal Observatory of Belgium. And then we have Professor Ronnie Keppens from University of Leuven. We have also 2 supervisors. We have Professor John Sundquist, and we have, I don't know if he's somewhere. Yeah, he's somewhere. Other supervisor, Dr. Dylan Key from National Solar Observatory from US. And of course me, my name is Jasmina Mangalenic. And after introducing all of us which are here, I would just like to mention that there are 3 jury members, committee members, which are excused because they were not able to participate today. However, they participate in the preliminary defense, and they also already asked the questions to Florian, and they were very happy with the answers. So that justifies the absence today. So that were Professor Len Dessine, then Professor Joachim Puls, and Dr. Asif Uddullah. So, after introducing the committee members, I would like to ask first Dr. Ronnie Bloom to ask questions. So I would like to invite you to ask questions to Florian.
Use a microphone. Well, first of all, I'd like to congratulate you on this impressive work. It's the way it combines the theoretical development with the numerical work is what has impressed me most of all. And I should say I'm also very grateful for the detail you put into the analytical development. Because I do remember at the time when I read these early papers that studied the instabilities, I did have difficulty following them. And thanks to you, to your thesis, it's a lot easier, and I can at least not finally understand what they were talking about. So thank you for that. Of course, as always, the remaining questions, and I have a few of those. Starting off with the distinction between the O-type stars and the B-type stars in their clumping properties. So you calculated basically 2 models, but in the chapter itself, you mentioned the growth rate, which depends on the effective temperature to the 4th power. So that sort of leads to the question, would I not expect already to see effects across the O-type range? One of the indicators you did is the X-rays. So would you not expect the X-rays to be diminishing for the cooler O-type stars?
That's an interesting question, actually. So, yes, there is this dependence on the temperature to the power 4, which is surprising. At the time I was studying this, I did not really pay attention to this because it was just there and was like fine. But so recently we have collected some more observations from stars, all stars, from a large-scale survey done by Kelly. And he actually also finds in the observations that the temperature, the degree of clumping, so which is a result from the growth of the instability, is strongly dependent in the O-star regime for the variation in temperature. So the hot O-stars show higher degree of clumping than the cooler O-stars, so say between 40,000 Kelvin and 30,000 Kelvin. You see actually more or less, if I remember well, a linearly decreasing function of clumping as a function of temperature. So that seems to be also an observational thing. Now, how does this relate to the X-rays? That's something I actually don't know. So in the, as it suggests, we should see less X-ray emission, and at least soft X-ray emission from cooler O-stars than from hotter O-stars. But whether that's only purely dependent on this to the power 4 dependence on temperature, I'm not sure, since there's much more going on in order to create the shocks and the X-rays in a model. And so I think it's more a question than on the spectral type, so the luminosity class of the star. So within the O-stars, there's the supergiant and the dwarfs. I think there you might actually do see a difference in the X-ray fluxes that are generated and presumably like this instability if they're single stars, which is not often the case. So I think there we should see it, but since I'm not familiar with the X-ray literature, I don't want to be the authority and make here a conclusive answer on the X-ray fluxes.
Yeah, it's good to see that there's at least some elements, observational evidence that show that there is this gradient that is across the different. Let me move on to the next question. This is about what basically causes the instability. So in the work you've been doing, this is always caused by, well, some intrinsic instability. But of course, we know that on the surface of the star, there's all kinds of things happening. You do mention some of this in your thesis. There's also, of course, the non-radial pulsations, which most of these hot stars have. So what consequences would these this different driving mechanism of instability, what consequences would that have for the structure of the star?
Yeah, no, that's a fair question actually. So we assume here in our models all that a hydrostatic photosphere, so a star that's just not moving, and it's an intrinsic process in this from the force we add in the equations. And in reality, of course, the star is not static, so you can already see this by looking at the sun. So if you have, for example, processes like the pulsation of the star, or even some turbulence created from deeper down in the atmosphere of such a massive star, there will be structures that will rise protrude into the photosphere. Now the question is, so if we take away the instability, are they the root cause of the clumping we see in the wind? Well, my personal opinion is no, because something needs to push it away and fragment it across the full star. So I think what in reality, whatever reality needs is happening, is that we have indeed these photospheric or subphotospheric processes like waves in the photosphere, pulsations, whatever, that are driving material into the somewhat higher atmosphere, and there the instability, because these parcels are still subject to the Doppler shift, will actually set in and just kind of let these structures grow even more. So it takes basically the structure that might be created from these processes is just is being helped by the instability physics to grow to even larger scales and become quants, at least in the non-magnetic case. That's my take on it, at least.
Okay, and then the final question is, I was thought I could go a bit broader than that. So I'm coming back to the theoretical development versus the numerical work. What I notice in my corner of astrophysics anyway is that there's very little of that theoretical development there. There's a lot of that numerical work. That sort of started me thinking, what would be the reason of that? Is that because well, after all, after the theoretical work, you still have to do the numerical work to see how the instability develops? Is that because it is insufficient in a certain sense to understand what is going on? Or is it also because theoretical work is quite difficult? I think so. The moment you use the word obscure for one of the things you wanted to say, is that perhaps the reason? Is it maybe something in the education that university no longer learn to do these kind of things? So that's sort of the question that came to mind, and I wonder if you could comment on that, on this sort of balance or imbalance between analytical development and numerical work.
That's, so I'm not going to answer the last question, so that opinion I keep for myself. Well, yes, so first of all, you need someone crazy enough to do the calculations. And I think there is part of the problem because it's a slightly obscure topic. So it doesn't draw a lot of people, like, for example, exoplanets draw people. So that's, perhaps you can blame that on the education, but whatever. On the other hand, that's just purely like manpower doing things. I do think that there is a limitation to the theoretical work you can do, because the mathematical analysis is just a stability analysis. So that means you're studying how linear waves propagate through your medium. Now that's a linear wave, so at some point, if there's an instability, this wave will grow, so it will become non-linear. And then your mathematics says, sorry, I cannot help you anymore. So you need a computer then for that regime. So there's already an inherent limitation in the theoretical development, because mathematics has only so much power to do it for you. And then of course, you need someone to do it. And that combination was not so unique in the past 40 years. So this has led to this dichotomy, I would say, between numerical simulation, which is easier because you just need some force prescription for this instability, and you need your favorite hydro code, and it's almost plug and play. Well, for the computations, you need mathematics, and I do think that mathematics is taught less well nowadays in universities, but that's my opinion. So you get less people with less correct skills to tackle the problem when they started teaching. I also had to learn it more or less from scratch. So the first lockdown was really nice for that, actually. So that's my answer on this kind of dichotomous problem in our field.
Okay, thank you.
We go to the professor on campus, please.
Okay, thank you. Yes, Florian, let me also, I can use exactly the same words as wanted. In terms of congratulations, this kind of work is out there. Excellent quality. I loved reading it from beginning to end, and I learned a lot during, so congratulations. You also gave a very nice presentation here. But on slide 6, you actually were introducing the different types of stars and their winds. And so you were talking about how the sun is, in your perspective, boring because it's just the wind. And then there's the radiation-driven part. But then you use 3 pictures on that slide of exactly the same object, namely the sun. So, you should, so you cheated, right? But you I would like to, let's say, here. So this is not an OB star, it's the sun, just in a different wavelength. But what about this suggestive presentation? I mean, are there, I don't know, local or instantaneous effects in the atmosphere of the sun that would actually relate to this LDI mechanism that you is that at all completely, to be excluded on the basis of, okay, you can never have these kind of temperatures, these combinations, or can it actually happen?
In the sun, I would say no, because what you need is a strong enough outflow. So the sun is not luminous, so it's not really the heat here, it's the luminosity of the star that's driving a radiation driven or light driven.
And during a flare, there's a very hot burst of luminosity.
Yes, and I think what's then the key important is how fast is the flare in this case or something else, the ejecta, moving. Compared to the sound speed in the sun. So is it very supersonic? Is it almost at the sound speed? So it's escaping at least. But I think here the real issue is the different attained velocities, which is quite different between the sun and the NOV star. Because it's the Doppler effect in the end that you really need to make this process happen.
No, it's just because you cheated.
I know.
Now, one thing that I obviously very much appreciate is that you used code that I'm also familiar with, NTIMR1. You actually used and contributed to this whole code, so thank you for that as well. Now, a code is always in development, just like theory and insights are. So, from your perspective, now having done this whole, series of work, what is sort of the type of algorithmic or maybe the type of physical or user technical improvements that you would suggest to the developers to which you can count yourself, perhaps also for further improving this code? Can you maybe say something about that?
Yeah, well, there are many things. We need more people. But no, so regarding the physics is there, so that's not really the problem. So I would say there are two main key issues, at least issues that should be tackled. And that's first of all, the way we do the radiation transport calculations in the model. So what we essentially do is that we trace photon paths through the wind. Now the problem here is because it's a non-local process, so information far away from the star, and needs information closer from the star. So this non-locality is an issue. And I think this leads to excessive computation time if you go to higher dimensions. So my first suggestion I'm thinking of is to kind of try to parallelize the way we do the radiation transport calculation. Now we're solving multi-dimensional integrals, space and frequency and angle. So I think some of them can actually be parallelized on their own, perhaps even in a hybrid way, using both distributed and shared memory parallelism. Now that's very hard to do, but I do think the next step is the way we do the rays, especially in the multi-dimensional models. That would be, I think, directly amenable to changes by just solving every ray on a different process.
I agree with your assessment. We need more detail.
Yes, no, that's clear.
During the preliminary defense, we also talked a bit about how this line-driven instability and also the Abbott waves, etc., how they actually fit in what I call the standard way of doing spectroscopy in both hydro and in PhD. So in hydro, if you just take a medium that doesn't do funny things with radiation, etc., you have sound waves. I'm using them right now. You have them in the forward and the backward direction. You have them in the shear waves. You have an entropy wave. I noticed that, to my pleasant surprise, we have an appendix now with also like the magnetohydrodynamic frequency. So can you maybe share some insights here as to how are these things linked? Is there something to be learned out of the very anisotropic behavior of some waves? Can you say something briefly?
Yeah, so first of all, I want to clarify for the audience that spectroscopy in our language is studying eigenvalue solutions, so it's nothing to do with spectrum. So yes, indeed I included Friedrich diagrams at the end, because they're actually quite interesting. So compared to regular hydro, yes, no radiation, you just have sound waves, backward, forward. So including this specific type of radiation force actually modifies how these sound waves are propagating. They actually become very anisotropic. So the inward propagating waves are faster, as they are the average waves, than the outward propagating mode. So there's already, by inclusion of this force in regular hydro, so no magnetic fields, there's already a strong anisotropy in wave motion. Now, if we include the magnetic field, so what I noticed when I was making these Friedrich diagrams, actually also the magnetic waves become, in certain limits at least, very anisotropic. So in most cases, they follow what I would call the standard textbook examples of magnetic waves, the alpha wave, fast wave, how they propagate. But in certain limits, compared to this radiation effect, this added wave, they're actually strong anisotropies, and the wave actually start to beam into very specific directions.
Are your simulations sampling those specific regimes at all, or you can probably try it?
Yes and no. So here's the problem: is to investigate that effect actually properly. What we need is in our multidimensional models also a multidimensional treatment of the radiation transport. I have started working on this, but there are no models on that yet. But then, yes, we would be able to study this.
Maybe going further on this, you have these very sophisticated multi-dimensional models. You even give a hint of 3D work on board, or maybe already finished, I don't know. As you know, these are significantly costly to perform in terms of supercompute power, etc. needed. But you will always be limited by whatever resolution you throw at it. So can you say something more, even though qualitative or quantitative, about if you could afford a tenfold increase in resolution, what statistical properties do you expect to actually hold up? Is your clumping factor going to be the same or an order of magnitude different? What kind of things do you expect to change the most, and what do you expect to stay as it is?
Yeah, so in the case that would be possible, if you would increase the resolution by a factor of 10, which we can't afford, so there's some limitation on that, which I explained. But so if you do this, so I've done some tests in 1D where we can actually afford this somehow with some more time. So what you find is that there's just more structure formation because you're resolving the shocks much better. Because your cell sizes become smaller, your instability physics is resolved better, and so you will see more growth overall in the wind happening. So that's a morphological change you'll see in your numerical simulation. Now, does this change the outcome of statistically predicted quantities like the clumping factor? No, actually not, because the average wind density, for example, that we need for such a model is still remains still the same. So it will not be exactly the same, of course, as a lower resolution model, but there's now a factor 10 difference, even on a factor 1.
Comfortably, yeah. And maybe, as you said, ultimately the thing is truly 3D. Now the magnetic fields that you use in your 2.5D models also have some symmetry, right? You just put a dipole and you hope that's not the actual field. If we learn from our sun, which we used here 3 times, then the structure of the magnetic field is way more complicated. It's not a dipole, and in the physical appearance of active regions, belts, etc. So they're both variations in altitude and longitude. How do you think that might affect your outcome? Again, will there be, I don't know, I think also your 2.5D simulations already show some indications of differences between equatorial, mid-latitude, and polar regions. Can you comment on that? What do you expect?
Yeah, that's a good question, actually. So the simple answer is I don't know, but it's not very satisfying. Now there is this thing that actually, yes, the way the magnetic field appears in the stars like our sun or our massive stars is quite different. So they're in the sun quite chaotic mainly, but they're basically related to the activity cycle of such a star. In a massive star, we don't have something like that. So the interior structure of the massive star is radiative. And now we don't know where this field is coming from, but we do know that it's actually almost a perfect dipole in all magnetic massive stars that we know. The large scale field doesn't know anything about the small scale, at least not sufficient enough to say something about chaotic fields near the surface. So the models I showed with the dipole is on large scale perfectly fine to model what we think should be going on. Now, if we include more smaller scale fields, that's a quadrupole or an octupole field, additionally to this dipole field, yeah, there will be regions with more confinement, so you'll have also at other latitudes closed loops, some kind of small magnetosphere. How that overall affects the generation of these pancakes, for example, I have no idea.
So lots of things to study.
Yeah.
The final thing, we have the James Webb Space Telescope for PhD community. How does that affect your field? What will James Webb Space Telescope learn your model?
Well,
What do you learn then?
yeah, so it's an infrared device. So we need UV. So I don't, so
It's useless?
yeah, no, I will not say that, also since this is on YouTube. But no, I think, so for the wave physics, so you can learn some things also from the watching the infrared. But since most of the flux is in the UV domain, you will learn most information from the UV. So for massive stars with physics in particular, I'm sorry to say, I don't think WSD will be that great.
Okay, no problem. Thank you very much.
Okay, thank you. So I will now invite our online
participant, Dr. Dilanki, to ask questions. Do you hear us?
Yes, I do. You hear me?
Yes, thank you. Please.
Okay, great. Well, first, of course, congratulations. You know that I'm very pleased with all of that's happened over the last 4 years. So, yeah, I guess the first question I wanted to ask here is related to this question of smaller scale magnetic structure and potential substructure there. I've been thinking more about these models that we've been running of bright spots on massive stars, and then the resulting sorts of larger scale features. And I was interested in your take on what we might find um, in in the clumping properties from bright spots, and then also the clumping properties of magnetic spots, and whether we could distinguish whether or not these discrete absorption components of CIR-like structures potentially in massive stars are magnetically formed or not based on clumping properties.
Yeah, that's a long question.
So yes,
So, yes, so to start off, so yes, we indeed investigated recently the emergence of small-scale fields from such a massive study. Was actually, which should be caused by a small convection zone, which is below the surface. And we studied how the wind interacts with this. So what we found is if you have a small scale magnetic field, it can actually lead to a spot. So there's a spot emerging on the star. There's another sunspot, so it's not dark, it's actually a bright spot. So we peek deeper inside this one, which means you see more flux coming from that specific spot. So our models show that when the wind is interacting with this spot, you actually get larger scale structures, more or less co-locating interaction with these, like in the sun, that are being generated. Now, these are large scale features. I'm sorry I cannot show you. You kind of have to imagine what's going on here. So the question now, of course, is do we need an origin like something exotic like small scale magnetic fields to explain a different type of wind structure? And that's a very interesting question, which I think I'm not entirely convinced of that we need something like that. Essentially, if we have the 3D model, which I showed you in the thesis, I think if we have rotation there, what happens, so the clumps collide, of course, in the radial direction, but they will probably, or they might at least also start to collide in the lateral direction, so the horizontal direction. And then you still get some kind of merging of clumps, which may eventually produce one larger scale type of structure, which is reminiscent of such a spiral arm rotating around the star, which is thought to produce to generate this type of specific feature in the absorption component of specific resonance lines. So that's my answer on that.
cool. Yeah, I haven't, like I say, it's been something that's sort of been rattling around in my brain. So be test those things out as good. Yes. Well, I suppose the other question, which just because it hasn't come up yet, you've been looking at the effects of various types of stellar properties on clumping properties, and I was wondering, you're moving on to bigger and better things now, but or at least other things. But for the folks who come after, what studies are you? What studies would you want to see done? What do you feel like you've left undone at this point?
Oh, well, I think I have a list of at least 12 things I want to do. So I think first of all, what should be done is to actually compute from our numerical models now synthetic observables in any favorite domain in the electromagnetic spectrum if you want. For example, X-rays, as Ron earlier mentioned, to compare this with observations, to actually see whether the numerical models are producing something reasonable or not. Because if not, then somebody after me will have to go back to the drawing board and figure out what's going on. Are we missing physics? Are we doing something wrong in calculations, the way you do the calculations? So I would say that's a low-hanging fruit to do because models exist already. The data is there. We just need another person that can make synthetic observables from these models. So that's the first thing I would do. And of course, In terms of model development, there's plenty to do. So I already alluded to the other one that the way we do the radiation transfer is one thing that could be really done in a better way, at least improve that one, either multi-way or looking into the parallelization capabilities. So yeah, these are just a few things. I would at least do if I would be working on this more.
Good. Well, thank you. That's what I have, and I can pitch it back to people in the room now.
Okay.
And now I would ask second supervisor, Mr. Johnson, please, to ask the question.
Yeah, great talk, Florian. I'm not surprised, so I'm not going to comment more. I might comment later. On that part. So actually, I wanted to follow up a little bit on the discussions here, and also since we're so to say regarding this, you have become the lead person in this field now, right? So you're gonna have to help us with the onset future development. But I want to attach on something which was you couldn't put on and had asked. So Robin Bloom first asked about these non-static surfaces. And then of course, the woman asked what would be also doing. The next steps in terms of development of the code. And I would argue that that is actually a key improvement, which I think we can do, or we might be able to do, to actually model not just from the surface layers, but from deeper down, through, not of course through the whole envelope, but at least down such that we cover this little subsurface connection zone, because then we might get both things, the field motions and the API. My question is that, let's say that we spin up with such a project, and we're going to do this over the next 20 years. What are the first steps that we need to do in order to make this happen?
Well, there depends. You want to do analytical or numerical development?
Well, method, analytical and numerical. You can comment on each of them if you want.
Yeah.
Or on your method.
Everything is my favorite. So for method development, if we look at the analytical way, so you can again do a mathematical stability analysis by including the radiation, the opacity effects from this subsurface layer of the star in your analysis, together with what you already have to. And again, look at how the waves start to behave here. I would suggest you want to include a magnetic field in this first case, just to make sure that you know what's going on. And then the outcome of that, you could actually then start to check with a numerical model, which means you have to develop it, of course, in the first place. And I think there's one simple way and there's one good way, but the more complicated one to go here. And so the simple way, I would say, is to take models that Nico has been computing for ultra-A stars, which launch from this iron recombination zone, but then tailored, of course, to a no star, which I think is more or less also possible nowadays. So that structure, so that's below the surface of the star, you can actually use as an input to a wind model, like I showed here today, as a lower boundary condition. So you don't have a hydrostatic boundary condition anymore, but you have a time-dependent boundary condition. And this is actually possible to do in AMR to read in a time-dependent boundary condition, like for example, Nico's model. And then see how that material that's launched from below the surface starts to interact with the physics of the LBI. Now the real I would say that better, at least way to do it is to do together. So you start somewhere inside the surface of the star, and you have to launch your material, and you just stack on the wind. That's a more complicated problem, also the way the radiation transport is currently computed and this Nico's work. So that would actually mean we kind of need to reformulate the way we are doing it a bit to stitch it together with these subsurface simulations. And that's really a longer term project compared to the easier part where we have two separate simulations that come together in the other.
Okay, well, let's get to work.
Yeah.
All right, and then final question. And since now you're going to work with solvents as well, together with exoplanets. Huh? So, and of course, we're going to drag you back here from now and then so that you can continue here working with us a little bit as well on the side. But what do you think? What can you learn? Because I'm a big advocate that one shouldn't be so afraid that not everything is so different and one can actually I don't have any. You can jump fields if you call it like that quite readily if one just puts one minds on it. So what do you think? What can you learn? What are the main lessons that you will take from your PhD work into your new job, which starts next week, I guess?
That's true. I think this starts next week. Yes, so there's actually quite some overlap if you want to see the overlap. And that's not only on the wind physics, so of course we're going to cool stars, so like as shown here with 3 times the sun, there are actually different types of wind. But the kind of interactions are more or less the same. It's just on a smaller scale, in this case with a planet. So the wind physics is, although it's different, the dynamics is not so much different in terms of what's going to happen. And so I will usually work on magnetic planets, so which at least is suggested. Also dipole fields like our Earth. So I have worked on dipole fields of stars. So dipole field is a dipole field. So that's also the same physics there regarding the magnetic field. And then there's of course the planet as a wind outflow itself, because the radiation here from the cool star in this case is heating up the material. So some basic radiation transfer concepts that we have been working with many years are just also applied there, just with different labels and names. But the equations are also the same. And therefore, I would say, and I think, so my new boss was convinced about this, that there is so many overlap. You just need to be able to see it and accept that there is overlap. So don't worry.
No, I'm certainly not worried. Thanks a lot, Florian.
So I'm actually glad that this slide is still on, because as a solar physicist, even our sun is disguised here as a red supergiant or orbit star. Anyway, it shows that it's important. So I'm really glad. And also I'm very happy for your last final conclusion, where you state that theory has to be combined with observations, because this is something which we often forget. Also in the solar physics, we have always scientists which deal mostly with the theory and scientists which deal mostly with observations. And we sometimes forget that actually the key solution is to join these 2 things together. So I'm very glad that you came up to that conclusion also. So regarding the other things, I will just ask one more general question, which is now looking backwards, if you would have to do it again, your full PhD, with the knowledge you have now, what you would change and how would you change, and if you would change something?
Oh, well,
Yeah, are you?
This is perhaps the hardest question. Yeah. No, I don't think I would do something different actually. I'm very happy with what I did. I do think I would do something different in the sense if there was no pandemic. I would have been able to collaborate more with observational astronomers, which was not really possible now because one could not go to conferences and other meetings. So that I would probably have done different then, but yeah, that's an insight. Regarding the science itself, as it stands, I'm very happy about it. What has been produced. I would have thought perhaps something more magnetic, but yeah, well, there's only 4 years in the end. So yeah, no, I'm very happy about it. It's just, I think, having done more, being able to do more meetings with other scientists would have been a better thing if that was possible. But that's how it is.
Thank you. And I think actually your work shows that you were very happy, and we are also very happy with what you presented here today.
Yeah.
So, is there some question from the audience, maybe?
Thank you. Thanks, Florian. That was really, really clear. Very, very good talk.
Thank you.
My question is what asked by the jury. This is really annoying. So I want to come back to the magnetic versus non-magnetic comparison. So magnetic stars very interesting. Just to comment first is that the magnetic fields are not pure dipoles in observed stars. They do have a significant quadrupole component.
Okay.
And the question is that if we're going to learn more about these magnetic stars, what I think we need is time rotation resolved observations, and you want to compare to your observations. So what do you tell us as observers that you need?
Well, I would say, so specifically this, I think from our models, if we could compute some power spectra, etc., and try to get a measure on the amount of variability these pancakes might generate. And this is actually, I would think, I hope, depends on the magnitude that's coming out, might be something you could then see in photometric data from tests or any other device like that, to see whether you can actually find something similar signature in these, because that would at least then say something about the possible presence of pancakes. The environment is extremely complicated, of course, but that's one thing I would think of. Another thing, if that would be available, would be some type of polarimetry data, especially circular polarimetry or polarimetry from electron scattering, because then you could also try to constrain the size of, in this case, the pancakes, because we have now a 2D model, of course, so we don't know how it looks in 3D. Is it like is the star fully covered in a sheet at every point, or is actually in the azimuth some type of breakup, which, I mean, polarimetry would be able to tell you something, I guess, about that. So these are two things I think we can learn from the observation and we can give as an input to people doing observations.
Perfect, I completely agree.
More questions? There are some more questions.
Thank you for the excellent talk. My question was, let's say, a rather general question. So we have now these additional effects, like these line shadowing instabilities, the magnetic field. How close do you think we are actually now to, let's say, the truth? Are there still, let's say, large effects, large physical effects that you're still missing, or it's now just tweaking and with your observations, just dial in some parameters?
So regarding the wind physics, we're pretty complete, I would say. So there is not so much improvement anymore you can do. Perhaps so we're doing isothermal models now. We still can include the energy exchange in the wind, which might be important for some diagnostics and like X-rays. So the major improvement is more going back to the question of Jan, that we want to get rid of the hydrostatic photosphere, and how that then, that's really a new thing. That's a large thing we're currently missing. And I think that's just for general, even without magnetic fields, an important step forward in modeling the wind outflows of massive stars. So there's certainly still a lot of things to be learned, but for the wind physics, I would say we are more or less there.
All right, thank you.
Some more questions? Okay, if there are no more questions, I thank you for a moment. The committee members will withdraw to make the decision.
Ladies and gentlemen, dear colleagues, I will now proclaim the result of deliberation by the examination committee, appointed by the doctoral degree in science, astronomy, and astrophysics. Mr. Florian Driessen has presented to the faculty of the PhD his PhD on the topic, the line disk shadowing instability and its effects on wind clumping for OB stars, and a partial fulfillment of requirement for the PhD in science, astronomy, and astrophysics. And he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been fulfilled. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Florian Driessen the degree of Doctor in Science, Astronomy, and Astrophysics. And I close the session. First, congratulate you, Dr. Florian Driessen. Here is your degree. I think that the supervisor wants to give a small closing speech.
Mm-hmm. I hope Dylan is also still there because we.
Yes, I am.
Yes. It will take off in a while. So yeah, you can breathe, Florian. Even though it's hard in this room, it's getting warm, huh? You know. And these are very cold, so refreshing. Anyway, big congrats, of course, to you, Dr. Driessen. And I must say that,
Sounds nice.
yeah, it sounds nice. Huh? And I must personally say that, you know, quite seldom have I experienced a title so well deserved. That I say in all honesty. And yeah, it's been actually, essentially from my side, 4 years of constant productivity, curiosity, professionalism, you name it, also during lockdown, as you mentioned. You did some of your best work during lockdown. And of course, a lot of fun, at least for me and Dylan. So it's also, it's really been great. And actually, it's been more than 4 years since I also had you as a master student, right? So we started this already back then. And I do remember when we first started to discuss a PhD for you, coincidentally, it was after the computational methods course, which, you know, Ronny teaches together with me then. And we actually, that year, we had a guest lecture on the, by Stan Walkie on this radiation line-driven instability in massive stars. And I remember you said to me after that, oh, but these are cool. Perhaps we could do something about that. So I think it's it's pretty safe to say that indeed, yeah, that we did something about that, and you certainly did a lot on that, and we have heard that a lot from the persons here as well. But yeah, it's safe to say that your knowledge about this radiation instability now has greatly superseded both that of your supervisor, and I would say also, I dare to say it, of your original inspiration that came from Stan. I would say that you are now you can consider yourself the world-leading expert in this piece of physics, in astrophysics. So that's quite an achievement, I must say. Now, the fact that you had this idea already during your master thesis, and then you basically just set out and did it, and that characterizes you quite a lot. You know, okay, but then you just go ahead and do it, and then you actually want to do it, which not always is the case, but for you it's certainly,
almost always the case. And that also shows your great initiatives, and that's reflected in other things as well. For example, you have mainly supervised a couple of two master thesis projects here at KU Leuven, right? And actually both of them in the aftermath led to peer-reviewed publications in ANA. And that's also quite an achievement in addition to your own stuff that you should be proud. I did see that one of them was actually also here on watching the talk today. So you certainly made an impact there as well. So that's great. And yeah, of course, now you've gotten a lot of flattery, right? And I know that you don't always agree with this, and that you have some sort of tendency sometimes to, you know, even if it's like today, very sunny, it's a nice day, we're all warm, well, that's not so nice, but anyway, Florian has a way that sometimes, even it's in the best of days, he can paint a pretty bleak picture of the sky and of the future. Which leads to fun situations and some drama, and that's good because, as you know, Florian has a calm and somber personality, but certainly we can have some drama behind the scenes sometimes. So that's a nice addition, because you know you have things like, oh, I can never do that, this will never work out, and this will take us 10 years to do, but then it's very seldom do. For example, you managed to organize your trip to visit Dylan when he left us to Hawaii in the midst of COVID, and then you were suddenly there on the research grant, which never could have worked out according to you, but I think you were in Hawaii. You might hear some more about that. Yeah. And then, of course, just before the summer now, suddenly I got the message, oh, I have to cancel my trip to Korea because none of the simulations worked. And I'm like, yeah, but perhaps that's not the reason to cancel the trip to Korea. Yeah, but you know, I'm not competent enough to do this. No, this is not going to work out. But yeah, of course, you went to Korea, and you know, I guess that's also why you're wearing a mask today. But that's a different story. You gave a great speech there, and the simulations in the end they did run, which they normally do. So that's great. And then another occasion where this happened, where you're a little bit underestimated yourself, perhaps, was that when it was time to look for postdocs for Florian, he was like, yeah, but it's so difficult to get funding, you know, in our field. It's impossible. I'm never going to get it. I think I'm going to have to quit the new year from now. I'm going to have to start to look for something else. And then I was like, yeah, but perhaps you apply for a postdoc or two or something like that. Okay. And then you find this with a Leon, you know, not really in your field, like we discussed, but of course, people recognize knowledge when they see it and talent when they see it. So yeah, you actually end up getting the first post that you applied for. So yeah, also there, you exceeded your own expectations. So there's been a lot of these fun occasions. Now. So yeah, then going on that, you're dealing with a postdoc now, right? So you're moving back to the Netherlands, or you know where basically you grew up. Or I've learned that that's not really where you grew up, because this is now it's actually in Holland. I learned this from when I think we were discussing football or something like that, and everybody calls it Holland, you know. And then Florian, in his very calm way, said, you know, for us from the south, that's actually a bit insulting. Okay, but now you're actually moving there. So just to remind people, Dylan and I actually arranged something for you there. Unfortunately, it was very strange because we had to do a little bit detour in the shipping. So it's somewhere in the US, but on the way to you. But you get this now, and then this you can show to your future colleagues there.
It's a shirt. It says it's the Netherlands, not Holland.
Now, when you're actually moving to Holland, you can just to keep reminding people about that.
Yeah. Oh, it is a joke.
I hope so. And yeah. Now. So you have seen this now that Florian is quite skillful. I think we all agree on that, right? And that also goes again in pre-COVID time in our group. We had these occasions when we met. We also made fika, which is basically coffee and cookies, and then we took turn in doing this. And since fika is a Swedish concept, I thought, okay, I'm gonna make some nice kanelbullar, some kladdkaka, whatever you find in IKEA, But then Florian, of course, he being him, he made up very nice Japanese. I think it was a fudge somewhere, showing also that he has great skills in that. And I guess it was good that we closed them down for COVID, because I felt like when we ate them, okay, this is so good cooked now, so next time I have to do it even better. And then we would have just erased there. But it does bring you out, and that was for the other thing that Dylan and I talked about, and we give you, that we know that you enjoy these times and these cookings, and we thought that we don't really know how skilled you are in, say, in various cooking forms. So we thought that we just give you a little bit gift certificate. And since you have your apartment situations, we didn't really know where to give it first. So we picked a store which actually is present both in Leuven and in Leiden. So you can sort that out right now. So it's for your new apartment though. So you can start to that will be in your image. It's the house. But yeah, it's the house on the picture.
Oh, that solves all my issues.
All right, so now I've been talking a lot, so now it comes to an end, right? It's time to wrap up, and again, then my sincere congrats again. And in general, you know this, it's been a real pleasure these years, and very proud of what you have accomplished, and you should be proud of yourself. And yeah, even though perhaps you not always see it that way, remind that I'm very confident that your future is certainly very bright. So with that, I will, of course, we will do a nice segue to Hawaii by giving you these little souvenirs. I think they're supposed to be like this, and like this. And congratulations, Florian, and I leave the room for good.
Yes, well, I'll throw in a couple extra words here, but I'll keep it brief to let everyone get on to celebrating with you, Florian. Well, congratulations, of course, today for getting over this hurdle, but also for all of the hard work that you've done to get you here. And it's really been a pleasure over these years to go from being your supervisor to being a collaborator. And I know while you were here, you had said to me that this relationship between a supervisor and a supervisee is one that you feel is special. And so I know I speak for both myself and John by saying we're very honored to be the other half of that relationship. Speaking of that transition from being your supervisor to your collaborator, I want to echo some things there about your independence and your perseverance. This has really impressed me over the entire time we've worked together. And as all of the people who have been working in the department through COVID know, it's been, well, it's not just the people working in the department. All of us know this has been a difficult and really testing time, but it was very impressive to me. You really handled that transition to working from home with a lot of grace and really a lot of independence. You really stepped up and took charge of your research and pushed things forward. And then I figured, well, COVID, not enough of a challenge for you. So then I moved halfway around the world and made you deal with a 12-hour time zone difference too. So really been, I appreciate you rising to that challenge now. As you're moving forward, well, let me see. on that note of actually moving halfway around the world here, I want to comment on how much work and patience and perseverance you really put into getting here in uncertain times, and it seemed like every time we set a date, there was some sort of roadblock in international travel, some new variant, some closure of borders, or some new bureaucratic uh, headache or hurdle from either the National Solar Observatory or Leuven. And I just, that you got here is really a testament to how hard and patient and dedicated you were in working on that process. I felt like every time we set a date, something went wrong. Every time you simply picked a new date, met all the deadlines for that, got everything lined up, and then inevitably things blew up again, and you just picked a new date, met all the deadlines, were ready for the next step. So it's it really that's a real testament to you that you got here, and um, I feel like a lot of really great work done, and looking forward to a lot of great work in the future as well. Um, as you move on to your new position working on planetary magnetic geospheres, I'm confident that you will be making great contributions there as well, because you have real innate curiosity and a willingness um, to ask questions and to go deep in, push things as far as you can, and then to ask. And that's really been a big aspect of getting all this work done. Um, well, just 2 weeks ago, while you were at the conference, I got messages from you asking about this and that talk and proposing work that we could do based on things that you were seeing for the first time, and it's really impressive to me, and really yeah, it speaks to your flexibility and your ability to really take what you've learned and move forward and apply it broadly. And yeah, I mean, I could go on for a while. As, as you know, I'm prone to talking at length if let me, but I think I'll wrap it up there and just thank you again for your work and for your collaboration and for being an integral member of the team as a researcher, as a mentor, and as an organizer, making sure that we have a new meeting every week. So wish you all the best as you go forward, and once again, huge congratulations.
So normally I should also say, I don't want to make it long, but like I just mentioned, yeah, I do think as you clap again, I think later you should again clap for these two people as well, because indeed, actually, coincidentally started with Jan almost 6 years ago. He was just a new professor. I was just a new student here in the master in Leuven. And I actually never had the intention to become an astronomer. So I came from a more mathematical background. And I was actually planning to work with Ronnie in Ronnie's institute because I like plasmas a lot. And so somehow Jon managed to trick me into the astronomy institute, for which I don't regret it. So I'm very grateful that things worked out like it was. And yeah, like you said, so I think these were very interesting views. I have certainly learned a lot. I also made a lot of mistakes, I know. For example, the frequency integrated linear test, which you have probably explained 20 times to me, and after the 21 times, I still made a mistake. So thanks for that perseverance as well, for keeping up with patience for me making mistakes. Of course, it was also nice to have actually a co-supervisor, so I can really tell everyone you should do this, because a co-supervisor is a nice way to ask all-done questions without bothering the supervisor. So then the supervisor thinks you're extremely smart, which actually you just learned everything, the correct answer from your co-supervisor. So I'm very grateful to that. It was very nice to have a young pair of supervisors as one of their first. So I'm Florian the third, but they were the first one. So I hope I gave both of you a nice time. At least it was for me very nice. I also want to thank the members, the jury here today. So Ron, yeah, so you were part of it where it started, but I would choose somebody else in the end. So sorry about that. But also Ronnie Glover, so from the observatory. So there's a small massive star group in the institute there, and I actually sincerely hope that we could collaborate more on topics together. And that was actually one of the reasons why I also wanted you to be in my committee, because I do think we can do much more. It's just that we need to see each other, and we're so close between Leuven and Brussels. So I sincerely hope that we have some more collaborations in the future between our institutes. And of course, Yasmina, thank you for the chair. We actually met 4 years ago at the Sesra Summer School. We were together in a picture, but of course you didn't recognize me. So, but thank you for being the chair. That was very nice how we handled everything, even last minute with me having problems here and there. So thank you for that. Having said that, so there's a reception next doors for everyone here. I invite you to that. Thank you very much.